Guess we'll get started. Today we're privileged to have some visitors from Scotland who are representing a company called Power Delivery. And they have a very exciting technology that promises to extract usable energy from ocean waves. And they're going to tell us about it today. And our talker will be Max Karkas from Power Delivery. So take it away, Max.
All right. Thank you. Thank you, David. So yeah, I'm delighted. Oops, sorry. Is that okay there? Delighted to be here and tell you a little bit about ourselves, our company, a little bit about what we're doing here in terms of the wave energy resource and what the sort of practical considerations and economic considerations are with this kind of technology. This isn't quite Web 2.0, this is possibly Energy 2.0, looking at new renewable energy options and what may be the sources of energy into the future. So this strange long red thing is our product. It's called the Pelamis Wave Energy Converter, and it's used for converting electricity, used for converting wave energy into electricity. You may wonder why it's called Pelamis. Pelamis is the name of a surface swimming sea snake, and when you see it, how it operates, I think you'll probably find the name is quite apt. So moving on, I'll tell you a little bit about ourselves as a company. First of all, just so you get a picture of who we are. We started in 1998, so a good while ago actually, and we've grown steadily since then. We're currently over 70 employees, and really covering all the disciplines that are required to deliver this as a technology. Very heavily focused on engineering. The engineering disciplines covered are things like mechanical engineering, structural engineering, control systems, electrical engineering, hydrodynamics, mathematical modeling, naval architecture, offshore engineering. And increasingly, we've been expanding our production side as we're moving from being a technology developer through to being a manufacturer. And so on the production team, we've got now 24 people and very much a focus on bringing this technology through into manufacturing. Just to draw a couple of names there and experience, Stephen Harrison, our production manager, he formerly was with General Motors, with Saab in Sweden, and obviously brings a lot of that experience. Really, the challenge in renewables is to make things, as we say in Britain, as cheap as chips. You've got to really get the costs down, and the only way you can do that is through volume. And I think the automotive industry is a very good example of that. And so it's great to have him on board and help drive that forward. So to move on, again, to give you kind of a flavor of what we're doing as a company before we get into the resource and how our technology works. If you look at the electricity sector, there are generally companies that make generators, and then there are companies that develop projects, and there are companies that then own and operate those projects. So if you think of wind turbines, there are companies that make wind turbines, companies that go out and find sites and go through the permitting process for those sites, and companies that then will go and own and operate those projects. And we see ourselves very much in this box here, which is to basically deliver the technology to assemble machines, install them, and provide operations and maintenance services for those projects. We don't really see ourselves as project developers or owning wave projects. A lot of people think, oh, you're into wave energy, you're about supplying wave energy electricity to the consumer. And in fact, there are plenty of people who do that kind of thing. So our objective is to sell machines to energy companies, to utilities. And it's really the best use of our capital. I'll come on to that in a moment, but we're venture capital funded, and that money is very expensive, and so we're trying to deploy it where we can best deploy it, which is on the technology. And really, by focusing on these aspects, by being at the heart of the assembly and commissioning process, it means that we can ensure the quality and performance of the product. A lot of people say, well, why don't you just license this technology? But it's not really a technology which lends itself to licensing, certainly at this stage in the process. We've got to work very closely with suppliers to bring them along with us, and particularly get to drive down costs as we go forward. It also allows us to secure and expand the intellectual property as things are going forward. And we think it's a very scalable business model as well. So how we've been funded this time, we're not yet profitable. We've been going for 8 years, which I think is quite an achievement in itself. Well, we've managed to secure a range of investors over this time, which you can see up here, ranging from more industrial investors like General Electric and Norsk Hydro, the Norwegian oil and gas company, to more purely financial investors like 3i, and Sustainable Asset Management, which is a Swiss green fund, very much focused on green technology and investment. So we've had some government support through this time. We've had about $5 million UK government support for some of the technology development program that we've been doing. But on the back of that, we've managed to bring in about $50 million of private sector contracts and investment. And that's how we've managed to fund where we are today. But I have to say, it's not always been a smooth path. Sometimes it's been a little bit close to the edge. So the starting point for this, really, I guess, if you look at energy policy, there are three legs to energy policy. And these are the kind of three legs. And this is a UK perspective, but it really applies to any country's energy policy. Clearly, they're increasingly so the environmental challenges in terms of mitigating the effects of climate change. We had quite a milestone report the other week in the UK, a report called the Stern Report, which sounds appropriately stern, and in fact it was appropriately stern. And it really highlighted the potential cost impact of climate change going forward in the future, and how taking measures, paying for things now to mitigate those costs is actually just a very sensible economic decision, let alone a very sensible moral decision, an environmental decision. So clearly that's one of the key drivers behind the development of renewables. Also, there's the security of supply aspects. One of the nice things about renewables is that you're looking at an indigenous energy resource that is local and not subject to the vagaries of distance and different political systems. In the UK, again, just to give you a UK perspective, we've had a big move here from coal-fired generation to combined cycle gas generation in really quite a short period of time. And that's allowed us to meet our Kyoto targets because gas-fired generation produces a lot less CO2 than coal. But this dash for gas that we've had is a little bit of a shame because we've just become a net importer of gas. We've been an exporter for quite some time. We've just become a net energy importer, an importer of oil and an importer of gas. And by 2020, it's reckoned that we'll be importing 80% of our gas needs in the UK. And that has to come from further and further afield. And in fact, the whole of Europe is looking to import more energy. And the question is, where does it come from? Certainly, Norway still has a reasonable amount of gas, but a lot of it comes from very long pipelines from Russia and the Middle East. And then the other aspect is socioeconomic. Clearly, conventional generation has hidden costs in terms of the impact, not only climate change, but also things like acid gases. What you see in this context is renewables becoming increasingly competitive, things like wind turbines, and indeed the potential, industrial economic potential in building the new industries of the future in terms of jobs and exports that can secure. And I think one of the nice things with renewables is you've got absolute price certainty going into the future. You've got no uncertainty about what your future fuel costs are because the fuel is inherently free. The thing that drives the price of renewables projects is really the capital cost in the first place. So it's against that context that we're moving forward. And here's another little statistic here. In the EU, there's a requirement to invest $1.1 trillion in the electricity sector over the next 30 years, mainly to replace existing generation capacity. It's quite a big figure. Now, in this context, I think what's a very big success story has been wind power. Today, there's something like 58 gigawatts installed of wind power. That's 58,000 megawatts. And it's been one of the fastest growing sectors in the electricity generating industry. And countries like Denmark, which were the first to really commercialize the technology, I guess, in a sustained manner, have a fair number of people employed in the manufacture of wind turbines. Similarly here in California, in fact, in Tehachapi, there's a reasonable production facility there of wind turbines. And in line with this growth in the market, the costs of generation have fallen by about 80% as the technology has been refined, developed, productionized. And again, you only have to wind back, a few years ago, and wind turbines were seen as very much sort of brown sandals and rice kind of approach. Very nice rice here, by the way. They're now the big boys involved. You know, the people like the Siemens, the GEs of the world who are involved in this market. If wind is such a great success story, why would you want to bother with something like wave energy? Well, first of all, it's a huge energy resource that at the moment is almost completely untapped. If you look at this picture here, what this is showing here is energy densities in kilowatts per meter. Now, just for comparative purposes, if you take a square meter on the ground of solar energy, you've possibly got about 100 watts per square meter of solar energy. If you take a square meter window bisected by a wind turbine blade, you've got perhaps 1,000 watts of energy available in that square meter. But off the coasts of Europe and of North America, you've got energy densities ranging from, say, 20 to 70,000 watts per meter width of wave energy. So it's a very concentrated form of renewable energy. And really what happens is, what wave energy is, and shouldn't be confused with tidal energy, wave energy is ultimately created by the sun, and it's the transfer of energy to the sun that creates the wind, and it's the transfer of wind across the oceans, it's that time average transfer of energy to the sea that creates waves. So basically, wave energy is stored concentrated wind energy. And some numbers here that are quite interesting to look at this. If you take the world resource and then constrain that down to the technically and economically recoverable resource, in other words, applying a variety of constraints to that, the World Energy Council have estimated that the potential world market for wave energy would be something like 2,000 terawatt hours per year, which is broadly equivalent to the existing nuclear or hydroelectric contribution to world electricity. Like with all of these things, there's never a magic bullet that solves everyone's problems, but certainly the potential for that is to displace an awful lot of CO2 emissions. If that market was developed, that would be broadly equivalent to the current emissions from the US electricity generating sector. If you take California as another example, again, taking the total resource and then constraining it down to what might be practically acceptable, these kind of figures here have been looked at, which could provide something like 20-25% of demand. And you'll see that the resource is really concentrated in the northern latitudes and the southern latitudes. And indeed, that's where a lot of the industrial applications are for this. There's another zoom into the US wave energy resource. This is produced by EPRI, the Electrical Power Research Institute in Palo Alto, who've looked at the sort of total US resource and the opportunities that exist there. Another nice thing with wave energy is that it's also a very forecastable energy resource. With one of the difficulties with, maybe not less so here in California, where the sun seems to always shine, but one of the difficulties with solar energy and with wind energy is that conditions can change quite quickly and be quite difficult to predict. With wave energy, because it's this time average transfer of energy to the sea, waves change very slowly. So what you're seeing here is a forecast here, a 5-day forecast. This is actually from a website called Lola, which is a surfing website. They've got very good graphics, actually, which is nice to use, which shows the wave height here and the period, the time between wave crests. And it's the two together that give you the energy in the wave. It's the wave height squared multiplied by the period. And what you can see here is that the waves develop out in the mid-ocean, and you're cycling through here a number of days, which actually you can't really see here, but it's cycling here through 5 days here. And you can see that it takes a number of days for those waves to reach the coast. So you can actually measure wave height with satellites. There's NASA have got various satellites that measure wave height. And there's a whole network of wave buoys around the coastline that store historical data for wave height and period. So But as I said, one of the nice things is that the resource actually changes very slowly. We've done some work with BC Hydro in Canada looking at how the resource changes on a sort of 3-hourly period. And if you did what's called persistence tracking, if you said in the next 3 hours, we just produce what we've just produced in the last 3 hours, in other words, no forecasting at all, you find you're within about 5 or 10%. So with a bit of gradient tracking, a bit of forecasting, you can probably hit it on the nail. And this is important for electricity grids. Electricity grids want to know what they're going to be producing in the next hour, what they're going to be producing in the next 24 hours. But beyond that, what they're going to be producing in sort of 3 years' time is of less interest in the sort of daily management of the grid. So what we're looking at is offshore wave energy. And if you look at wave energy concepts, there are a variety of different concepts. There are some that are shoreline-based and some that are offshore. And what we mean by offshore is getting sufficiently offshore in order to capture most of the energy, or the highest amount of energy that's available there. If you look at this graph here, you can see water depth here. This is water depth here along the x-axis against wave power. And what happens is the waves travel for many thousands of kilometers across the ocean without losing any energy. But when you get to about half a wavelength depth, that's where the wave, which consists of a series of orbiting particles, starts to touch the bottom of the seabed. And that's where you start to progressively lose wave energy. So the best point to be is round about here at around about the 60, 70, 80 meter depth contour, and our machine sits on the surface there to capture most of the energy. If you're on the shoreline, you've potentially lost a lot of your wave energy. Now, those of you that are surfers will know that waves tend to pile up as they come into the coast, but you've actually, although the wave height gets larger, they're actually becoming compressed, so you're actually losing energy. The other thing is that it's also quite a destructive environment on the coastline. If you look at the picture on the top there, you get these crashing breakers on the shoreline, which are not very pleasant. And whereas if you go a bit further out to sea, and you have a more benign swell, I think you can say. So just to reiterate, the waves that we're looking at are the deep swell waves. So you're looking at wavelengths of typically 100, 120 meters between wave crests, and time periods between those wave crests of anywhere from 8 to 18 seconds, that sort of thing. And that deep swell wave really is the same all the way, is very similar all the way up the coast. So a project like this doesn't need to be in front of a prime surfing location. The bathymetry that produces good surfing waves is totally different to what you need in terms of good wave energy conditions. And to give you a context of how far you need to go out to get to that depth, the picture here of the UK shows where the 50-meter contour is. It's this orange to green area. And generally speaking, on the western-facing coast, you're looking at distances off the coast to get to that depth contour of anywhere from 2 to 20 kilometers. And here in California, the kind of locations that one would look at are generally speaking of that order, sort of 5 to 10 kilometers off the coast. And one of the nice things with that, I guess, is that it means that you have a minimal visual impact. If you're standing on the beach looking out to sea and there's any appreciable swell, it's actually very difficult to see our projects. I'll come onto the technology in a moment, but you'll see that the machine actually has quite a low freeboard in the water. And again, these are things that always have to be looked at in a power project, but we think we've really got a minimal environmental impact. Of course, we're biased, but we really think that the technology has potential to be one of the least impact technologies in generation. We've got no greases or fluids in direct contact with the seawater, so we're very unlike a ship with its prop shaft in the water, and we've got no rapidly moving equipment or machinery that might upset things. But that's not to say that you shouldn't go through the due process to make sure that any particular site that you're looking at doesn't have any particular features that would be of concern. And that's something that we're very focused on as an environmentally aware company. One of the questions that... sorry, you were going to say?
Is there any reason you couldn't go further than 60, 70 miles offshore?
Not 60, 70 meters. Yes, the question was, is there any reason why we couldn't go to deeper water? And the answer is no. The reason you don't really is because the extra cost of submarine cable isn't really getting you extra benefit. But there are applications where you might want to be further out in sea. And really, all you're doing there is having a greater mooring length for the machine. And indeed, it actually becomes easier to moor in deeper water. And the question I was asked at lunchtime actually was that you know, this technology has been around a while. I've seen some patents from a long, long time ago, and you know, so why has it not already happened? You know, and some of you may remember in the UK we had some wave power research done in the 70s, and so people say, you know, why is nothing happened? Well, I think, you know, one of the big changes since then, since the 70s and equally since the 1700s, is that the offshore oil and gas sector, somewhat ironically perhaps, has gone out and developed a lot of the basic technology building blocks that just didn't exist back then. And what our focus has been is to try and utilize that technology, whether it be wet mateable connectors, electricity connectors you can connect underwater, or whether it be the mooring dynamics or operational experience, and really utilize that technology and apply it in this different area of wave energy. So really, the conclusion of the study I'm quoting here really said that there were no major issues that couldn't be addressed through technology transfer from other sectors. So finally, onto the concept and the machine. The machine is actually an articulated cylinder, which you can see here in profile on the side, and also a top view here from the top. What happens is the machine is moored at its nose, and it self-orientates into the direction of the oncoming waves. So a bit like a flag on a flagpole or a ship at anchor. Waves then travel down the length of the machine, and in doing so, each section articulates both up and down, and also side to side. And that movement is resisted by hydraulic rams, which pump high-pressure hydraulic fluid through smoothing accumulators, which evens out the rather lumpy input energy into a nice smooth flow of hydraulic fluid that turns a hydraulic motor and generator. And the nice thing about all the component technology is that it's all pretty much off-the-shelf technology, which has been tried and tested in this kind of environment. Really, the concept is what's quite different to anything that's gone before in wave energy. But the actual component things, what you want to avoid as an engineer is to have prototypes within prototypes within prototypes and really kind of, you know, stick on one thing at a time. So the machine consists of 4 long sections that you can see here, and separated by 3 smaller sections, 3 what we call power modules, which I'll show you in a moment. And the complete machine is 140 meters in length, 3.5 meters diameter, so about the size of 4 train carriages, with a rated power of 750 kilowatts, which would be similar to a wind turbine, a modern wind turbine of maybe 6 or 7 years ago, and would provide sufficient electricity for about 500 households. Now, the idea with this is that you deploy it multiple machines in what would be called a wave farm. So similar to a wind farm where you've got multiple machines connecting together and sharing a common cable back to shore. But what we have in the machine, these power modules here, this is one of these power modules. So just going back to the previous slide, there are three of these here within the machine. They're connected together electrically. But what we've got is, as I said, we've got this movement that's occurring. We've got 2 hinged joints, one that's a substantially vertical direction and one that's in a substantially horizontal direction. And that movement is resisted by these hydraulic rams here. So they're effectively just like big pumps. They're a bit like a mobile power pack that would be used on a crane, but we're kind of using it in reverse with some funky bits and pieces in there as well. But, and you can see the hydraulic motor there. These are the smoothing accumulators, which are kind of like a pressure vessel. It's a bit like if you imagine pumping water up a hill to a tank. What we're doing is we're storing sufficient energy in the machine to even out the wave-to-wave variation so we can produce good quality, power into the grid. And this 2-axis thing is an important feature of the machine, how we control the response of the machine to maximize energy capture, particularly in smaller waves in the summer. So I'll move on to that in a moment. But the key thing for a wave energy converter above everything else is to be survivable. And again, in the past, people have perhaps approached this from the wrong direction. Some people have looked at how to be the most mathematically efficient to capture a meter width of wave energy. And actually, that's not the most important thing. The most important thing is to be survivable. And in fact, what directly follows from that is the economics, because that's the other most important thing, is to have the best cents per kilowatt hour. And that's really the reason the machine looks the way it does, this kind of strange, long, snake-like object. By pointing into the waves, it gives us excellent load-shedding capability in the extreme waves. But what we're trying to be is be very closely coupled to the forces that are there most of the time, the buoyancy forces, the hydrostatic forces, buoyancy versus weight, but be almost invisible to the very large hydrodynamic forces, the drag and slam loads that occur in extreme waves. And what you can see here is the machine in different sort of sea states here. And as you can see in the larger sea states, what happens, and it's a physical property of the machine rather than it being a sort of add-on system to do this, is that the machine just cannot continue to go up the wave. It starts to go through the wave and locally submerge and re-emerge through those wave crests. And so what we call this is hydrostatic clipping, where the power of the machine, the energy absorbed by the machine, the movement of the machine is limited by the wave height. And again, this is similar to wind turbines, where you feather the blades in high wind speeds, because it's not worth capturing that energy. It only occurs for a statistically small amount of time. And if you were absorbing that energy, then you'd need to throw lots of steel and concrete at the machine to make it be able to cope with that. And of course, that has a negative impact on the capital cost. You're then throwing lots of money at things. So if your concept is inherently survivable, then that directly translates through into the economics. And so being too short to react against extreme storm waves is sort of key to this. Now, I can probably show you some video that perhaps explains this or gives you a slightly better feel for it. You can see that this is some tests here in a wave tank here of one of our prototypes. And the nice thing in wave energy is you can get very good repeatability from a wave tank to full scale. If you imagine this machine being 3.5 meters diameter, these are some quite big waves. And what you can see in the top here is the output of our numerical model. We've got what we believe to be the most sophisticated numerical model that's ever been developed for wave energy. Many lines of code going into that. And this is the graphical front end, which is, of course, great for things like this, because showing you reams of data is perhaps not so interesting. But you can see the machine, how it basically goes through the waves and how it reacts against itself. The machine is not yanking against the mooring. It's not using the mooring as a source of reference. The mooring really keeps it on station. So the machine will pull back in big swells, but then recover as the swells pass. So what you can see, the bit sort of sticking down there is what we call the mooring yoke. And this is the bit that attaches the mechanical and electrical connections to the machine. This is another sort of frontwards look at the machine here. And I should say the numerical model here is just actually getting the same data as was fed to the wave makers here in the tanks here. As you can see, there's pretty good repeatability between the model here and the wave tank test data. It's, as I say, it's a model that we're very proud of because it allows us also, of course, to model lots of different things for the future in terms of increasing energy capture and sort of novel designs going forward. But you can see it is a pretty biological type of movement. So I think that the name Pelamis is quite apt. And again, you can sort of see it going through those waves there. So in terms of power capture, you remember that I showed the power module has both a vertical and a horizontal component. Now what we can do, because waves are harmonic in nature, they have a periodicity, and you say that to an engineer, you start to think about resonance. And it's actually quite different to most other energy sources. In fact, I don't think there really is harmonics in the kind of delivery of most other forms of energy. And so what we can do is we can tune the machine to the predominant wave condition. If you look at a typical sea state, it may be characterized by a period between wave crests of a sort of 10-second sea with a significant wave height of 3 meters. But then over time, over several hours, that may change to being a 12-second sea state. And what we can do is we can change the natural frequency of the machine to be tuned to that. And the way we do that is we can restrain the rams in different directions. If we restrain in the vertical direction, we produce much more of a side-to-side movement on the machine. And in fact, this is why the hinges aren't at sort of perfect angles to the sea. They're actually at a sort of drunken angle, because if you give things an escape route, then you've got somewhere for things to go. If I push down on this pen here on the table, it's got nowhere to go. But as soon as I give it an escape route, it'll shoot off to one side. So what we do in the summer is that we can control the system when the waves are small to produce much more of a side-to-side movement and therefore capture a lot more energy than would otherwise be the case. Whereas in the winter, we have much more of a vertical movement. The other thing is that this system, because it's this really gets into the theory, but if with all wave energy converters, there's something called point absorber theory, which is really at a point you can capture a width of wave energy. And it may seem slightly counterintuitive, but you can capture a width which is actually much larger than the point that with which you're capturing that energy. If you've got a point absorber or a buoy that can move in one direction, if you go through the maths, the maximum energy capture that point absorber can capture is something like the wavelength divided by 6. So a wavelength being of the order of 100 meters or so, the theoretical maximum energy capture is that wavelength divided by 6 multiplied by the kilowatts per meter width. In our case, we are a little bit like a phased array of point absorbers, and a bit like a sort of radar antenna. We can tune that so that we can capture a lot more energy. So the theoretical maximum energy capture of our machine is actually a wavelength over 2, which essentially at the end of the day means we have a very high power capture per unit volume, per unit weight of the machine. We're nowhere near that theoretical maximum at the moment, but it's nice to know that we are nowhere near it, because obviously there's a lot of room for improvement moving forward. And this perhaps gives you a little example here of resonant response. There's some early tests here, but as you can see here, the waves are quite small, but we're getting quite a lot of movement on the machine. I'll show you that. Let's see if I can show you that again. You see the waves are coming to you across here, and they're really quite small, but you're getting a lot of movement there through the restraint. And another example of tuning, a tuned response here. These are images from the Carbon Trust website. If you get a chance, have a look at that website. And this really shows that an energy converter with this is showing the sea state here varying. This is the spectral density. This is the wave spectrum of the sea and its variance with time, and this is what it's trying to represent. Something with a fixed tuning ability obviously is not able to capture as much energy as something where you can vary that. The trick's to be able to vary that as quickly as possible with the sea state, and that's really where it gets harder to do, because there's a lot of control that goes into that. But potentially through improving the software over time, we think we can capture a lot more energy, which gives us a lot of confidence in the future. So a bit about technology development. As I said, we've been going. Yeah, sorry.
So a quick question. So does it sound like you've got smarts on board and you're tuning on board?
Yes, that's right. We tune, but at the moment it's a fairly coarse tuning algorithm. So the sea state's changing it changes slowly, but if you were God and you could see each wave by wave, then potentially that's where you want to get to in the longer run. So this is a bit on the concept development here, how the technology is developed over time. The nice thing is you can do a lot of testing in wave tanks. We've tested at 80th scale, at 50th scale, at 33rd scale, at 20th scale, and 7th scale. And what you're doing is you're testing all kinds of different things. You're testing survivability, you're testing mooring dynamics, you're testing energy capture, and you can get very good repeatability from wave tanks through to full scale. And what we undertook to do ourselves was to fully understand and test each of these aspects before going to full scale. And again, in the past, people have tried to jump too far too fast. And you've got to take these things one step at a time, and we've tried to ensure by doing that. So before we got to a full-scale machine, there were 2 or 3 key steps that we did. We built an intermediate-scale prototype, which is this 1/7 scale prototype at the top here, and we tested that at sea in the Firth of Forth outside Edinburgh, where the waves tend to be about 7th scale as well. And that gave us a very good feedback and confidence in going forward and to build a prototype, because you can do that at that scale and do things at modest cost without making big mistakes. But what this 7th scale machine, which we built in 2001, didn't do because of the scale, was produce electricity, because at that scale it's just not worth it. You can model the energy absorbed, but it's not worth putting generators on that sort of scale of machine. So the other part of it was to build one of the power modules that I was talking about earlier on land, and to test that fully on land. And it's much the same way that you don't test a jet engine for the first time up in the sky. You want to test it on land first. And so we had a 2 megawatt power connection coming in here, driving a hydraulic power takeoff system that then acted around this fulcrum here, and then our power takeoff system then converting that mechanical movement back into electricity. And not surprisingly, there was far less electricity coming out than was going in, because otherwise we'd really have solved something. But, it gave us very good confidence in the overall power takeoff system and the efficiencies that we were getting with the power takeoff system. The overall mechanical to electrical efficiency is of the order of 70 to 80%. And I think I've got a little bit of video of this. I'm afraid it's a little bit stuttery, but this is the typical sort of ram speed that you'd see in the sea. It's not a sort of very rapid, splashy kind of movement. It's quite a slow sort of process. Remember, this is time periods of 10 seconds between wave crests, so it's a very sort of slow process. These are the hydraulic power packs that go inside the machine that convert that energy into electricity. You can sort of see it again there.
70 to 80% loss or 70 to 80%
Efficiency, yes. Yes. It's some funky bits in there. And then the third aspect that we did before we built a full-scale prototype was go through a full design verification. Now what this is something that's quite common in the offshore oil and gas sector. If you're developing a new bit of kit, you get it verified. And nobody asked us to do this, but we thought it would be a very good idea to do it ourselves, to have the design independently verified, to look at the extreme loads and fatigue loads over the design life of the machine. These machines have to last out there for 15, 20 years. And you've got to look at the fatigue and you've got to look at the extreme loads. And this is what Atkins did. Atkins are specialists in offshore engineering and been involved in a lot of the structures in the North Sea. And this was an 18-month process where they looked at all of our design, slightly frustrating for some of our engineers because they kept wanting to put more steel on things, quite a conservative process, but ultimately I think very rewarding because it meant we fully understood everything that applies through that. And this is really taking offshore design codes, Det Norsk Veritas and American Petroleum Institute offshore design codes, and applying it to this machine because there are no design codes for wave energy converters. So we're trying to use as much as possible what exists at the moment. As I say, this looks at the extreme loads, so you define a 100-year wave condition. This is what you'd normally do in the offshore oil and gas sector, and you apply factors of safety to everything based on that. What's different to this compared to the offshore oil and gas sector is clearly we don't have explosive hydrocarbons on board or people. So it's arguably less of a requirement to be as high a level of safety. But equally, because this was our first machine, we wanted to make sure we were applying the best possible standards. So it meant, for example, the steel thickness in the machine is about 1 inch thick to really be kind of belt and braces, as we'd say in Britain. But this, again, is part of the reason why costs are high initially. And what this has allowed us to do is secure insurance for the machine, commercial insurance, which is obviously a key part for commercial development. Somebody wanting to buy machines wants to know that it can be insured. And at the end of the day, that's the bottom line. If it's insured, job done, then they're happy. And what we wanted to do was educate the insurers. You've got to get the insurers down a learning curve. You'll know with a car, you have your no claims, but I presume you do. In the UK, we have a no claims bonus. If you don't crash it each year, your insurance premium goes down. Same sort of thing applies here. And then this is this 100-year wave. This is a 28-meter wave, which is the sort of extreme wave condition that was defined at the time for the machine. And this is a big wave. So I don't think a wave like that has ever been recorded at Orkney, where we've tested the prototype, but it gives you an idea of the kind of the process that we're testing against. So you could sort of summarize up this technology development as sort of from this to this. But sorry, your question?
The ocean's a very caustic environment, and it's sort of like, I don't know, I was trying to figure out if it's like sealed around these joints or something like that.
It is, yeah. Well, we've got double or triple seals actually between the inside and outside of the machine. So all of the equipment inside the modules is completely dry.
I guess where the hinging happens.
Yeah, indeed, yeah. And what we've applied here is the sort of best possible offshore experience. You know, there's offshore structures and ships that have been out there for many, many years. So use epoxy paints to offshore standards, and as I say, to be honest, even if you didn't have paint with inch-thick steel, it does actually last quite a long time, even in a salty environment. And then this is the full-scale machine here. Oh, it's kind of jumped a bit there. Under test. Now, this machine, as I say, it's the size of 4 train carriages. It, with its ballast, it has sand in it as ballast, about 300 tons of sand ballast. The whole machine weighs about 700 tons. And when you think of moving that on land, it's actually very difficult. But here at sea, it gives you a real impression of the energy that's there in the waves that can be utilized. And here's another one at nighttime, just so you get a flavor for it. And you can see it's a very, it's quite a benign sort of movement. It's not this sort of rapid thing that you might imagine that of things kind of splashing around. So I've kind of just run through these points here. I've talked about survivability and the power capture, using available technology, very important. Having a hydraulic power takeoff system being very well matched to the resource. Waves are characterized by very high forces, but relatively low velocities. So that kind of ram speed there is an ideal match for hydraulics. And that also allows us to smooth the power. Because we have these hydraulic accumulators, these pressure vessels, we can store energy in the machine for several minutes, which evens out the kind of lumpy input energy to produce smooth energy and good quality energy. And the nice thing from our point of view is that we've been able to patent the whole device concept because there isn't really anything like this. So you can patent the whole device concept. Something like a wind turbine, unfortunately, you can't really patent a fan on a stick. It's sort of been done for a while. And independently verified, not just by Atkins, but by a number of external parties who've been casting their eyes over the technology. In terms of the resource, as I mentioned, it's a very forecastable output with negligible visual impact. We believe minimal environmental impact, but we're happy to be put under scrutiny. And then 2 vital points, I think. We have no construction on site. So again, in the UK, we've got a big program on offshore wind, building wind turbines offshore. And full marks to that. I hope it's very successful. But equally, I think what's quite different with our technology, the machines are built off-site. We deploy the mooring system from the back of a boat when we choose to do that, and then the machines are brought to site. So we're not trying to construct these machines out at sea. And then equally, we don't try and do any maintenance on site either. If you send a guy offshore to go and tighten up a bolt, it'll cost you maybe 10 times what it will do on land. So we think it's much better to bring the machine back to shore, a bit like bringing your car to the garage rather than trying to bring a garage to the car. And the advantage of that is if you can do that in a fairly short period, and we've got a rapid attachment system, it means that statistically the weather windows when you can do that are much more frequent. If you need to spend several days or hours out at sea, the time when the conditions allow you to do that are statistically far less frequent. So coming to more down to the economics and how you look at this technology in terms of the power production, what you go is the first thing to do is establish the resource at a particular location. And as I mentioned, there are wave buoys off the coast which record this data. NOAA, National Oceanographic Administration, and whatever it's called, has data on all of these for lots of different. So I'm sorry, I don't know what the abbreviation stands for, but has data for these sites here in different locations. And what you can see here, this is through the year here, the kind of wave energy increasing, and this is variance between 3 years here. So you can get a feel for the resource variation across the year. Now what you do is you build up what's called an occurrence table for a particular site. So you'd look at the wave period and the wave height, and you accumulate that data over the year, and you'd say, okay, I'm in this box for 5% of the year, I'm in this box for 2% of the year. And what this particular thing here is we call our power matrix. So we're saying what power we would produce in each of these sea states. So if you take the resource data at the top and multiply it through our power matrix, which is what we believe we'll produce in those sea states, you come up with an overall energy characteristic of the energy that would be produced by the machine. And clearly it varies because in the summer the waves are smaller and in the winter the waves are larger. And what we're trying to do is capture the most energy and the most economic cost through that. A little bit on markets, because I think it is important to talk about the markets. We've got a technical challenge, which is to deliver a technology that works and works reliably. We've also got a commercial challenge, which is to find the right partners in which to work with, develop projects, sell machines, etc. But we also have a political challenge as well, which is to try and bring to feeder markets forward that can allow this kind of technology to come forward, because any technology always starts high and it has to find a route through here, through to deployment. What we're trying to do, I was just saying earlier, is perhaps what any business school would tell you not to do, which is to bring out a new product in what's a commodity market. You know, the electricity that comes out of the socket is just a commodity. So it's not, there aren't really, or there haven't been to date, early adopters who will go out and buy, wave power electricity because the electrons are blue or whatever. It's not like buying the latest kind of mobile phone or that kind of thing. So you really need government to take a lead in trying to bring forward these technologies if you're going to get them out into the market. I'll come on to that a bit more, but where we're focused initially is markets that are more than 20 kilowatts per meter, with these kind of market enablement measures for wave energy. And really, in particular, at the moment, the focus is on two particular locations, which is the UK and Portugal, where these measures have been established for a while. But increasingly, we're starting to see these things come forward in different locations. And this really comes back to what I was just talking a moment ago about, in terms of cost. If you look at all of these technologies, they all have a cost profile against the deployment into the market. And what this is a log graph here showing cumulative megawatts installed against cost in terms of, I'm sorry, it's in pounds, but in pounds per kilowatt. So this is just looking at the capital cost of a project, how much it costs to build it in the first place. And what you see is that photovoltaics have seen a tremendous cost reduction since the early 80s through to the sort of present day. And this kind of learning process, you see typically a reduction in cost of perhaps 15 to 20% for each doubling in capacity. So as you get to the far right of the curve, you need proportionally much more capacity to really drive these costs down. I mean, these learning curves are very similar to not just to power production, but to mobile phones or computers or oil field development. You see very similar sort of cost projection. It's all about the volume. And if you look at wind turbines here, initially a rapid rate of learning and then kind of flattening off a bit towards the right-hand side. Gas turbines, a huge period of development in the aerospace and maritime sector before they could be used for electricity production. So it's a slightly unfair comparison here. The first gas turbine was really the jet engine in the Messerschmitt 262 in the Second World War, and it had a mean time between failure of 21 hours. But the average flight combat time was 7 hours, so I guess that was all right. But you compare that today with gas turbines with mean time between failures of many thousands of hours. So again, I was talking about offshore wind. In the UK, we've got a big program for offshore wind. And in terms of its deployment, it's perhaps over here on the left-hand side of the scale. But in terms of its basis of technology being onshore wind turbines, it's perhaps arguably more on the right, which means that to get the cost down with something like offshore wind, you perhaps need another 50 gigawatts to really drive that cost down another 15%. So what gives us tremendous hope is that our opening costs are over here on the left-hand side of the scale. Now, of course, there's no guarantee that we would follow a similar cost projection downwards, but I think it's a very good place to be starting. This is all kind of top-down approach, looking at the technology here. Equally, we've done a sort of bottom-up appraisal, looking at the individual components and seeing, do we have sensible assumptions on where those component costs could go in order to drive the cost down? And we do, actually. So we think that this has tremendous promise because of this, but the challenge for us is that the costs are up here at the moment, which is above the cost of wind, for example, above the cost of conventional generation, below the cost of solar. But we need a market in order to drive that forward. Now, capital cost is only one aspect. The thing that really counts, of course, is the cents per kilowatt hour. And to come up with the cents per kilowatt hour, you need to look not just at the capital cost, but also the cost of finance, what debt and equity go into the project, the length of the project life, what the cost of operations and maintenance are, and the cost of connection, and lots of factors that go into it. So it's a little bit more contentious when you look at cents per kilowatt hour, what actually goes into that. But again, for comparative purposes, this is what's happened with wind, a tremendous success story. But in the early days, in the 80s, the costs were right up here, and those costs have come down over time as the technology has been refined and developed. And our first projects are coming out kind of over here, in terms of the project we're doing in Portugal at the moment, is able to go forward. Our customer is able to buy machines because the government has set a feed-in tariff of around about 15 pence per kilowatt hour, which allows them to make a sufficient return on an early project. And this is very similar to what's happening in California at the moment for solar energy. There's a California Solar Initiative which pays a premium price. I think it's between 39 and 50 cents per kilowatt hour for the first 5 years for a solar installation. And that really allows the technology to be deployed, and hopefully the cost to continue to come down as that technology gets out into the market. So about the project, so you get a kind of flavor of it. This project we're doing in Portugal is with a company called Enersis, which they started off in hydroelectricity about 17 years ago, moved into to wind about 10 years ago, and they see wave energy as being the next sort of opportunity. They're a subsidiary of Babcock and Brown, which is a leading power company. And if you look at it from the Portuguese context, there's a big wave energy resource here. Portugal imports a lot of its energy, and that's a big driver behind it. I'm not going to spend too long on here because this is a little bit more commercial and possibly less of interest, but it's really a staged approach that we're looking at here. The first stage being a small-scale project, but then being able to expand that up to a larger project. And just to whiz through some pictures here of production. These are production of the modules. You can see here. This is inside one of the modules. These are the tubes, very much like wind turbine towers. You can see some of the fabrication here. Painted tubes. These are machines here being shipped out to Portugal. This is in Portugal. This is where we're doing the final assembly. We see we're using a kind of rail system here, which we then deploy the machines into the water. This is something called a habitat that we use for connecting machines up. This is one of the front of the machine. That's the Portuguese Minister for Economy, and some machines here ready to go out. We're also working on some other projects, but we haven't signed contracts for these yet. But we're working with Scottish Power here in the UK, and hoping to move forward with a 5-machine project with them soon. And also with another company off the southwest of Cornwall, a company called E.ON. But importantly, here in the States, EPRI has done a lot of great work in terms of looking at sites and potential application, particularly here on the West Coast. And we're very encouraged by that, and hopefully things will move forward on this front. And obviously lots of other places where we've got little toes in the water and hoping things to develop, but still a long way to go. Just quickly to say there are other opportunities for this technology, not just in electricity production, but potentially in desalination as well. You can use the direct mechanical pressure to drive a reverse osmosis system, and there are some other niche applications as well. So really, that's a very quick run through. I wanted to just give time for any questions if anybody has any questions. So thank you. Yes.
So I was just curious, sort of from the ocean navigation perspective, are these things installed in places that are marked on navigation maps, and have you done any kind of collision testing?
Yep. Yeah, no, that's a very good question, and I've just realised I've left out a slide on that. But the machine, as you can see here, this machine here off Orkney, there are actually 4 cardinal markers. They're called cardinal buoys that delineate the perimeter of the project, and the same happens in Portugal. And this is this is normal kind of practice for a marine hazard at sea. Whether it be a submerged rock or reef or oil platform or offshore wind farm. The site's delineated by 4 cardinal markers. These have navigational lights and radar reflectors on it. It gets marked on charts, as any other marine hazard would do, and in notices to mariners. So quite often there's an impression that ships kind of blindly go across the sea without really knowing where they are, but they have to know where they are because quite often it's foggy out at sea, it's nighttime at sea. They've got to know they're not going over a rock. The same thing applies here. The key thing for us is to be where we should be. So that's not to say that an incident might not happen at some point in the future. You know, we have car crashes, but we still drive. But I think the key point is I don't think the risk is significant. And clearly, you wouldn't site a project like this in a key shipping lane. There's plenty of locations where you can find a reasonable place for it to be located. Yeah, yes?
How do you anchor the mooring lines to the bottom of the ocean?
The mooring is a compliant mooring system. We have this yoke extending downwards, and then we have three chains that come off that and are anchored with mooring blocks and anchors into the seabed. So it's quite a small footprint on the seabed. The anchor blocks are sort of, this kind of size. I mean, they're big, but, not that big, as it were. Yes?
How many of these machines would be required to supply all the world's electricity needs?
All of the world's electricity needs, how many machines would it be required? A lot. And I don't think it would be practical to supply all the world's electricity with wave power. I mean, this is the thing in energy. There is no magic bullet. You need a range of options. But that market potential that I illustrated, I think, would be equivalent to something like, I think it's about 20%. So, it is a large energy option that could be utilized. And what would that be in terms of machines? It would be, depending on the size of the machines, which, we have a certain rating at the moment, but we intend to increase that over time. I guess it would be something like 600,000 machines. Yes?
Is there any particular reason there's 4 segments, not like 6 or 10?
Yes, there is a particular reason, and it's really an economic cost optimization. We originally, as you might have seen with the kind of yellow model there, we've looked at machines with more joints, and we looked at them with less, and you kind of optimize it to what makes most sense at the moment. But it may well be in the future that we have more joints. Yes?
How much routine maintenance is necessary?
That's a question about how much routine maintenance is necessary, and that's an interesting area that we're continuing to develop. The machine is inherently got a lot of fault tolerance because we have multiple generating units, each with double motor generator sets. If one of the generators stops working, it doesn't necessarily mean we have to pull the machine back. It means we've lost maybe 1/6 of our capacity, but it's not necessary to perhaps dive in there straight away because you're only getting full output in the full sort of sea condition. We have a strategy that's both reactive and preventative in terms of maintenance. And depending on, the machines are fully monitored. We have fiber optic connections to it and radar and wireless links, so we can fully monitor everything and categorize whether things need immediate action or whether there's something that can wait over time. But it's something that, if we knew what the least reliable component was, we'd make it more reliable, but we have to get more experience to establish that and improve over time as well. Yes?
How's the Portugal deployment going?
It's going well. We've been testing a new kind of mooring deployment system, which allows us to use very modest vessels for that kind of work. And so, as soon as we get that mooring system in, then the project will be up and running. Yes.
Do you know how much power could be taken from waves in the oceans before it started affecting the climate and currents and things like that?
The question was, do we know how much energy could be taken from the oceans before it affected the climate and currents, did you say? We've done some studies, and others have actually independently done studies on terms of wave energy abstraction. And a project like ours out at sea, obviously we are capturing some of the energy, but if you imagine an island out at sea, an island absorbs 100% of the energy that hits it or reflects it and absorbs it. Now, if that island is a kilometre off the coast and it's a kilometre wide, you're not going to have any waves there on the shore. But if you've got that island, maybe 10 kilometres out to sea, the waves reform and refract around it, and you still get waves at the shore, maybe slightly diminished. In our case, we're not like an island. We're not absorbing 100% of the energy that goes through a project, a wave farm. We're absorbing about 10% of the energy that goes through it. And the impact of that on the shore, with the typical distance that we've got, is actually pretty small. Whether there are any wider impacts with much larger deployment, I couldn't really say. I mean, that's something that would have to be looked at. But I can't immediately think of so long as you take a reasonable proportion and you're not absorbing 100% of the energy that's passing through an area. I don't think it would make a huge impact. I think the other thing is that when you look at storm conditions, our machine, as I was saying earlier, isn't designed to absorb that energy. So some people say these would be great to prevent coastal erosion. In our case, it wouldn't apply, because all of that energy in those extreme waves passes straight through to the coast. So you're still getting a lot of the sedimentation change and erosion in those kind of conditions, because we're not absorbing that energy. Okay, I think there's one more left. Yes?
What do you have to do to the power that comes out of this before feeding it into the grid?
Yes, perhaps I didn't mention, we've got the question was, what do we do to the power before it goes into the grid? We've got 3 power modules in the machine. They each generated 690 volts, 3-phase. And then we have a transformer in the nose, which steps the voltage up to a higher voltage for transmission to shore to minimize losses. In the case of the Portuguese machines, that's at 6.6 kV. So we've got a transformer stepping that voltage up. Power's fed down through an umbilical. Multiple machines share a common static cable back to shore. That then would feed into a substation, which then may again step the voltage up to feed into the transmission network. Okay, well, I guess that's it. Thank you very much.